Yes, do you have any questions first? Do you want anything repeated? Any example solved? So today we will be starting discussing electromagnetic interactions. So first let's study the classical problem. So what's the classical Lagrangian or the Hamiltonian of the system? For that, let's discuss with the Newton's second law. Now we know that the force acting on a charged object would be just Q times the electric charge times the E plus V cross B. E and B being the electric field and the magnetic field at the position of the particle. That will be a crucial, important point. V is the velocity of the particle, so the force kind of depends on the velocity. Now, one thing that you should notice is that since the force depends on the velocity of the particle, you cannot really write it as the gradient of some potential that depends only on the position. But in the classical mechanics, if you write the Hamiltonian as T plus V, V just corresponds, the force is just the gradient of the V, the potential. So we have to do something slightly different in the case of velocity-dependent forces like the Lorentz force. Now, the first thing we will do is we will just convert this force into an expression in terms of the potentials. You see, in electrodynamics, we can write the magnetic field as the curl of some vector potential, and then the electric field just becomes minus the gradient of the scalar potential minus 1 over c time derivative of the vector potential. And in fact, the origin of the gauge symmetry is basically these relations. You see, if you change, if A goes to A plus the gradient of some function lambda, the B field does not change. So B field, because the curl of the gradient is just 0. So the curl of A stays the same. At the same time, if you make a change, phi goes to phi minus 1 over c d lambda by dt. And you do both of these at the same time, the electric field also doesn't change. So under these transformations, B stays as B, and E stays as E. This is what we call the gauge symmetry, although we can change the scalar and the vector potentials as we wish. The physically observable quantities, the electric field and the magnetic field, they do not change. So this was the reason why, at least in the case of classical electrodynamics, we used to say that it's the electric and the magnetic field that have any physical importance. Now, the thing in quantum mechanics is that we will see, we have kind of hinted on some examples where, although the force is zero, the E and the B fields are zero in certain regions which are accessible to our particles, and hence my particle shouldn't feel those fields. We will see that quantum mechanically, nevertheless, there are observable effects. Now, let's try to express the force in terms of these potentials. Now, Newton's second law also tells me that the force is just dp by dt. Now, I will just use a slightly different notation. P, this is called the mechanical momentum. Which is basically, for a point particle, it's just m times v in classical physics. So dp by dt, this is equal to q times, well, the electric field is gradient of minus the gradient of phi minus 1 over c dA by dt plus v cross the magnetic field is the curl of A. Now let's just convert that double cross product. Now v cross the curl of A we can write this as the gradient of A dot V minus V dot the gradient acting on A. So these two things are different, by the way. Let me write it in this form, V dot the gradient of A. Now V times the gradient of A, sorry. Minus V dot the gradient acting on A. So dP by dt, this is equal to Q times minus the gradient of phi minus 1 over C dA by dt. So here I also have a V over C. And the Lorentz force, this is V over C. Minus 1 over C V times the gradient of A minus V dot gradient acting on A. No, sorry, this is the gradient of A dot V, sorry. Now let me just try to reorganize it a bit. This is minus the gradient of Q times phi minus 1 over C V dot A. You see, it is this term, the first term, it's over here, and this term is this one. Then I have other terms which are minus 1 over C Q times dA by dt plus V dot V times, sorry, what did I do? This is V dot the gradient. Okay, let me rewrite this. I just made a mess. So it is the gradient of V dot A minus V dot the gradient of A. And this is plus. No, that is a minus. V dot the gradient of it. This should be the final result. Now let us look at one more thing. dA by dt. The total derivative of A, the vector potential. They say this is, of course, when we are looking at the motion of the particle, we are interested in the vector potential at the position of the particle, not at an arbitrary point. At the position of the particle at the time t. And let's calculate the total time derivative. With time, A changes due to two reasons. One, due to the explicit time dependence. Second, well, my particle is moving with time. So at a given instant, vector potential at this point is important. At the next instant is the vector point at the next point that is important. So my point at which I'm evaluating the vector potential is also changing. Those are the two reasons why the vector potential that the particle feels will change with time. So this will be equal to, I will be just using the chain rule, it will change due to the explicit time dependence, or it will change due to the position dependence. This is equal to del A by del T plus V dot the gradient times A. So this is the total time derivative of A as the point at which I'm evaluating the vector potential is moving with my particle. So you see, this dP by dt is minus the gradient of Q phi minus 1 over C V dot A minus 1 over C, that line, Q times dA by dt. Okay, so apparently I made a couple of mistakes somewhere. Let me just correct my mistakes. Or maybe not. Or d by dt pi plus Q over C A is equal to minus the gradient of Q phi minus 1 over C V dot A. Okay, now we are almost done. Well, this just looks like in the form time derivative of the momentum P. This is equal to minus the gradient of some kind of an effective potential, velocity dependent effective potential, where this velocity dependent effective potential is Q times phi minus 1 over C V dot A. Now this P, which I defined as plus Q over C A, is called the canonical momentum. Then the Hamiltonian of my system, I can write it as, well, it's the kinetic energy, which is given by the kinetic momentum, P squared over 2m, plus the potential energy, Q times phi minus 1 over C V dot A. No, sorry, I don't have that term. This is my Hamiltonian of my system, where this kinetic momentum now is P minus Q over C A squared over 2m plus Q times phi. This will be my Hamiltonian that I will be using to study the motion of my particles in an electric and magnetic field. And you see this P over here, let's get the equations of motion. What is dx by dt? This will be equal to 1 over I h bar, commutator of h and x, which will be equal to 1 over I h bar, 1 over 2m, P minus Q over C A squared and x. This is equal to 1 over I h bar, 1 over 2m, Px minus Q over C Ax squared and x. Now basically A commutes with x, A depends on position. P, Py, and Pz, they also commute with x. It's only Px that will not commute with x. This is equal to 1 over I h bar, 1 over 2m, px minus q over c ax times px minus q over c ax x plus minus q over c ax x multiplied with px minus q over c ax. So this will be equal to 1 over I h bar 1 over 2m px minus q over c ax. That commutator will be I h bar. Both of them will yield the same thing. So 2I h bar, 2I h bar. So this is equal to dx by dt is equal to 1 over m px minus q over c ax. So the px appearing over here, which we represent as the derivative operator in position space, is not really the kinetic momentum. The velocity of the particle, which we call dx by dt, is related with what we define as, sorry, this is dx by dt. This is p, the capital P, not the small p. Now, another thing we need to pay attention to when we are writing, let's say, the particle in a, let's look at the particle in a magnetic field. Well, we can always choose phi to be 0. There is A. We have the gauge symmetry A prime, which can be written as A plus the gradient of some lambda, but it depends only on the position. So that with this gauge transformation, phi, which starts to be 0, phi prime still remains 0, because this phi prime is related to phi through the time derivative of lambda. If we choose lambda time independent, just the scalar potential does not change. So if we restrict ourselves to this gauge, now you see what we have seen over here, not what you have seen in electrodynamic courses, let's say. There are infinitely many scalar and vector potentials that you can work with that corresponds to exactly the same electric and magnetic field. All of them, they correspond to the same fields. And classically speaking, they all correspond to the same physical system. Well, similarly, in quantum mechanics, they should also correspond to the same system. And different vector and scalar potentials that correspond to the same electric and magnetic field, we say that they are related by a gauge transformation. It's always possible to find the lambda such that these different vector and scalar potentials will be related through this relation. So there is kind of an ambiguity. You can think of it just like your freedom to choose your coordinate axis. You see, the x, y, and z components of, let's say, velocity will look different in different coordinate axes, but they are all related with each other. So you just pick one coordinate axis and fix them, and once you fix it, a given velocity has given components. Similarly, in electrodynamics, there are infinitely many possible scalar and vector potentials to choose from. What you most of the time do is you just add additional constraints on your system so that you just pick up a unique vector and scalar potential. This is called gauge fixing. There are infinitely many vector and scalar potentials that correspond to the same system. You just pick one that you feel comfortable with. You are free to choose whichever one you want. And you can think of this condition that the scalar potential will be 0 as one of our gauge fixing conditions. We are not interested in all those possible scalar and vector potentials correspond to only a magnetic field electromagnetic configuration. We don't want to look at all of them, but we just, for the time being, we are looking at the ones that have zero scalar potential. Still, there are infinitely many scalar and vector potentials corresponding to B equal to B non-zero and E zero. There will be infinitely many of them, and they will be related by a position-dependent lambda. Now, the Hamiltonian of my system in such a case will be just P minus Q over C A squared over 2m. Now, if you want to write down the Schrödinger equation, for example, well, let me write this in this form also. This is 1 over 2m P squared plus 1 over 2m Q squared over C squared A squared minus Q over MC P dot A minus A dot P plus A dot P. Now this is, I also have a 2. You see, keep in mind that when we are talking about P dot A, when we convert it to a derivative, it will also involve the derivative of A. Now let's write the Schrödinger equation. You see, the Schrödinger equation, we started by this equation. This is I H bar del over del T alpha T0 T. Now if you look at the position, if you multiply with a position bra, this becomes P minus Q over C A squared over 2m between the bra and the ket I H bar del over del T psi of T. In the position state, we can write this as H minus I H bar, the gradient, minus Q over C A, scalar product with R, P minus Q over C A, alpha T0 T. I also have this 2m. This is equal to I H bar del by del T psi of T. Here I use that the position state representation of the P is nothing but my gradient operator up to that multiplicative factor. And if I use it once more, I get minus I H bar, the gradient of Q minus C A, scalar product with minus I H bar, the gradient of P, now gradient, minus Q over C A multiplying psi of R and T. This is equal to I H bar del by del T psi of R and T. This is our Schrödinger equation. Now, in this form, it's explicit that when you are taking this gradient on the far left, you have to also consider the gradient of A, the vector potential A. That is something you shouldn't forget. Let's do an explicit example. Let's imagine we have a cylinder, a hollow cylinder. Now, our particle is confined within this cylinder. So this is my box. This is my box. So you can just think of it as you take a rectangular box and just curve it into the shape of a cylinder. Our particle is not allowed to get moved out. So let's put some coordinate axis. This will be my z-axis. Let's say this is x-axis. This is my y-axis. The potential is, let's say the height is h is 0 if z is larger than h. Or now let's see, it is the VR is 0 if z is between 0 and h and rho is between a and b, and infinity otherwise. So there is this confining, bounding potential.
Magnetic field uygulandığı için sıfır oluyor.
No, there is no magnetic field yet. I just assume I have my particle in a box, but the box is not just a cube. It has this shape of a kind of an empty cylinder. This is the shape of my box. There are other forces acting on my particles which makes sure that my particle cannot leave my box. Now what I will do is I will just put some magnetic field inside. I will put a solenoid. So I will assume that there is a solenoid B of R. There is a solenoid inside of my box, so that B of R will be B in the Z direction if rho is less than B, and 0 if rho is larger than B. No, sorry, A. So what I'm imagining is, okay, I have this disk. Inside there is a hole going through my not this cylinder. Inside the cylinder there is a hole. In this hole there is a uniform magnetic field. Just to have a simple example. So since my particle is confined within my box, it cannot go to the region where there is a non-zero magnetic field. The wave function will also be 0 in the region where the magnetic field is non-zero. So classically speaking, there is no way that my particle will know that there is a magnetic field, and hence none of its properties should depend on the magnetic field. Now let's look at the quantum mechanical problem. Of course, to study the quantum mechanical problem, the first thing we have to determine is what is the vector potential. What is A? What is one possible form of A? Now, of course, outside B is 0. So curl of A should be 0 outside. Well, do you know how to solve this problem in electrodynamics? Well, let's see. We have to find a vector we have to find a vector potential whose curl is B. Now, most of the time, the direction of the vector potential, it just corresponds to the direction of the currents creating the vector potential. Now, if you consider the solenoid, the currents are running around the solenoid in the phi hat direction. So the vector potential will also be in the phi hat direction. Well, my problem has this rotational symmetry around for rotations around the z-axis. So and also translational symmetry along the z-axis. So that basically tells me that the magnitude of the vector potential can only depend on rho and not on anything else. Now, furthermore, since the curl of A is equal to B, I can just integrate this over some surface. But the surface integral of a curl of a vector field, I can write it as a line integral over the boundary of my surface. This is my left-hand side. The right-hand side is nothing but the magnetic flux. So I can use this relation to determine what A should be for the solenoid. So let me just look at from the top. So Z-axis is out of the screen. This is the region where I have some non-zero B. Here B is 0. Now let me consider such a loop. Well, you see, I have this relation over here. If you have any closed loop, if you integrate the vector potential around that loop, whatever your loop is, then it should be equal to the magnetic flux going enclosed by the loop. So that's my relation, and it holds for any loop. So it should hold for this particular loop also, since it holds for anything. Now for this loop, well, dl is just its magnitude in the phi hat direction. So dl dot A is just A of rho times dl. Now if I integrate this around the loop, well, you see, around this loop, rho is just constant. Since rho is constant, A of rho is also a constant. So I can just take it out of my integration. What remains is just the circumference of the loop. So this is 2 pi rho times A of rho. Now for this loop, the magnetic flux, well, the magnetic field is just constant. So the magnetic flux is just B times the area. And these two should be equal. But this tells me that A of rho inside my solenoid should be equal to B pi rho squared divided by 2 pi rho. Pi's cancel, rho's cancel, so this is 1 over 2 B times rho. This is, of course, valid if rho is less than A. Now we can repeat the same thing for a loop that goes around outside my solenoid. I will just repeat exactly the same thing. Now the only difference will be, in this case, the magnetic flux. You see, within this blue loop, the magnetic magnetic field is non-zero only in the disk with radius A. So whatever the radius of my blue loop, the flux going my blue loop is just the magnitude of the magnetic field times pi A squared. It is constant. I can make my loop larger, smaller, the flux doesn't change. But this means that A of rho will be B times pi A squared divided by 2 pi rho. And hence, I can cancel the pi's. I get B A squared over 2 times 1 over rho less than A. So this is my A of rho. And hence, in the region that I am interested in, A of rho is equal to B A squared over 2 times 1 over rho in the phi hat direction. No, sorry, this is rho larger than A. This is my A. Or in the original problem, this is A, this is B. The inner radius is A, the outer radius is B. Now, when I'm writing the Schrödinger equation, for me what will be important is minus I h bar, the gradient. You see, here I have my expression, minus q over Ca. Minus q over Ca. Now I know what A is in cylindrical coordinates. So if I use the expression of the gradient in cylindrical coordinates, let's see. If you just look it up, you will see that the gradient has the expression minus I h bar del by del rho in the rho hat direction plus 1 over rho del over del phi in the phi hat direction plus in the z hat direction del over del z minus q over c be a squared over 2 rho in the phi hat direction. So basically we can just combine this with the phi derivative minus I h bar times in the rho hat direction del by del rho plus in the phi hat direction 1 over rho del over del phi minus I over h bar q over c. Well, let me just write pi over there, phi b over 2 pi. I will define phi b as b times pi a squared, the total flux, basically, plus z hat del over del z. This is my, I mean, in the case of, compared with the free particle case, I have to replace, compared to the case with zero magnetic field, I just need to replace the phi derivative with this derivative over here. That is the main difference. And that additional term is basically just a constant. And hence, since that is just a constant, I will just say minus I h bar gradient minus q over c a squared. This will be, of course you can just take the, this expression, take the square of it, but just keep in mind that the derivatives with respect to phi of one of these factors will take the derivative of phi hat vector also. So you can either do that or just look up the expression for the gradient in cylindrical coordinates, Laplacian in cylindrical coordinates. This is h squared 1 over rho del by del rho, rho del by del t, del by del rho, plus 1 over rho squared del by del phi squared, plus del squared by del z squared. This is the Laplacian in cylindrical coordinates, but instead of the phi derivative, I will just use that expression above. So it will be del over del phi minus I over h bar q phi b over c times 2 pi. So this is my Hamiltonian operator, basically. If you divide by 2m, you get our Hamiltonian operator in our case. You see, although my particle never feels the magnetic field, because it's always in a region where the magnetic field is zero. It never penetrates into the region where there is non-zero magnetic field. Nevertheless, you see that the Schrödinger equation is modified. Well, let's try to see if this has any observable consequences. Like, for example, we can observe the energy levels. Okay, maybe that factor doesn't change the energy levels. We don't know. Now, as an example, we can just go ahead and try to solve this Schrödinger equation and see what are the consequences. Now, the way we will be solving this is, we will be using basically separation of variables. We will look for a solution I will be looking for the eigenvalue problem. We will be trying to determine the energy eigenvalue, so we will be trying to solve the time-independent Schrödinger equation. And the wave function, I will assume that it will have this form, a part that depends only on rho, another part that depends only on the phi coordinate, and a third part that depends only on the z coordinate. I will be looking for solutions of this form. And then I have my boundary conditions. Psi of r, when I evaluate that z is equal to 0, should be 0. Psi of r, if I evaluate that z is equal to h, it should be 0. These are the top and the bottom of the cylinders. And psi of r, when I evaluate that rho is equal to a, this is the inner surface, it should also be 0. And psi of r, when I evaluate that the outer cylinder, outer surface, it should also be 0. Because just outside the potential is infinite, so just outside it should be 0, and the potential has to be continuous. So just inside the surfaces, it should also be 0, because just outside it is 0. And these conditions basically tell me that this function z evaluated at 0 should be equal to its value evaluated at h. This should be 0. By the way, this h is the height. It's not the Planck's constant h. And this second set of conditions tell me that this function r evaluated at a should be the function r evaluated at b. It should also be 0. So these are my boundary conditions. And these, of course, I'm looking for a normalizable solution, etc. But anyway, the fact that it's confined to a finite volume and it's 0 on the boundaries will just cause the energy eigenvalues to be discrete. We will continue in the next hour. Now, any questions? Okay, so see you after the break.